Jacks. In this video we're going to be talking about some trigonometric limits. Now the first thing you need to know is if you're using your calculator or just working with trig functions in calculus, be sure that your calculator is always in radian mode. So we're going to assume that the input is in radians. In other words, all angles are measured in radians. Now we want to eventually get to the point where we can do some derivatives of trig functions. But before we can do that, what we need to do is we need to look at a couple of special limits that are going to be needed in our derivation of trigonometric derivative formulas. And the first one we want to look at is the limit as x goes to 0 of sine x over x. Now, as you can see from this graph in Graphmatica, it looks like that limit is 1. And of course we know if x is 0, this is a 0 over 0 form. It's an indeterminate form. The limit could potentially be anything just based on that. But in this case, we see the limit looks like it's 1 here. And of course, if we look at a table, we can also see that. So here we see a graph. Looks like it's coming into 1. Here's some table values putting in closer and closer to 1 here in the table. Closer and closer to 0 for x. And the y's get closer and closer to 1. So it looks like that limit is in fact 1. Okay, to prove that, let's see if we can work with this. Now to do this, we're actually going to end up using the squeeze theorem. And this particular picture is going to be important for us. So, we want to start by thinking of theta, let's say, as being some positive angle. And let's say it's already an acute angle. So if you put it in standard position, we're looking at an angle in the first quadrant here for the terminal side. Or in other words, it's an acute angle. And of course, if you let theta go to 0 from the positive side, this is the kind of angle we're talking about. Now I want you to look at this picture here. This red arc is part of the unit circle. So the point C can be the point 0, 0. The arc length here from 1, 0 as it rotates around to point B following a circular path is the length theta. The radian measure of that angle is that length. So that red length is theta. And we can clearly see that that's more than this green length, which is the sine of theta, because as we know, when we take any point here at A, we spin it around to point B, and we spin this array around. Now we have, it traces through an angle of theta. That's that red arc length. Then the coordinates of point B are cosine theta, sine theta. So this distance from C to D is cosine of theta, and the distance from D to B, this green distance here, is the sine of theta. Now it also turns out that if we go up a tangent line here to the curve, in other words, the vertical line x equals 1, and we see where the terminal side of this ray meets this at point E, it turns out that this purple length here, this side of the length from A to E, is tangent of theta. See, if you take that length over, for this angle, take opposite over adjacent legs, those lengths, this length from E to A, over A to C, is the tangent of the angle theta. Well, wait a minute. The length from A to C, or C to A, that's the length of 1. So this length divided by this length is just this length, and so this length here from E to A, this purple vertical length here on the tangent line, is actually the tangent of theta. It's a tangent line, is part of why it's called the tangent function. Okay, now, so I want you to look at this picture, and we want to convince ourselves that sine of theta is less than theta, which is less than tangent of theta. And this is going to be our key observation. Okay. One way to see this is certainly the distance from A to B, the straight line distance, is the shortest distance between A and B. And this arc length distance is even more than that. But the distance from A to B is the hypotenuse of this right triangle right here. So the distance from A to B straight distance is more than the distance from B to D. So we clearly see that theta is bigger than sine theta, and then we get it less than this tangent of theta here as well. So we get this in between. Now tangent of theta is sine theta divided by cosine of theta. So what I'm going to do is multiply all three sides by 1 over sine of theta. Sine theta divided by sine theta is 1. Theta divided by sine theta is here. And of course when I divide this by sine theta, I get 1 over cosine theta. Okay? Now if these guys are in this order, their reciprocals are in the opposite order. So cosine theta is less than sine theta over theta, which is less than 1. And so we get this relationship here. And so now we're set up where we have the expression we want in the middle squeezed in between or sandwiched in between two other functions. Now what we do is we just take the limit as theta goes to 0. 1 goes to 1, stays 1. Cosine of theta goes to cosine of 0, which is 1, as theta goes to 0. And so by the squeeze theorem, this is squeezed in between. Okay, so for theta between 0 and pi over 2, cosine of minus theta is cosine of theta, sine of minus theta is minus sine of theta, sine of minus theta over minus theta is sine theta over theta. So notice that we have this relationship here. So if we take a minus theta, then we'll be between minus pi over 2 and theta, and we get sine theta over theta is the same as sine of minus theta over minus theta, and that's going to be between cosine minus theta and 1. So we also get the same setup for negative angles. So if we're talking about negative angles but are positive angles that are close to 0, then, acute angles but positive or negative, then we take, that's the kind of angles we can talk about when we're taking the limit as x goes to 0, or as theta goes to 0. And so we get the squeeze theorem. Okay, take the limit as x goes to 0 here, I'll switch to x's, and we get this limit as 1. So that's a very important limit for us. Now there's going to be another important limit for us. We want to see what happens when we take the limit as x goes to 0 of cosine x minus 1 over x. Now, again, like as much of the time as the case, when we plug in 0 here, we get 0 divided by 0. Cosine of 0 is 1, minus 1 is 0. 0 at the bottom, 0 divided by 0. That's an indeterminate form, so we can't just plug it in there. We got to do something else with it. So we're going to multiply by the sort of the conjugate here. So here we have like a minus b, we're going to multiply by a plus b, which gives us a squared minus b squared. And of course you can multiply the top by cosine of x plus 1 if you multiply the denominator by the same thing. So we're using that special pattern that we've used before, a minus b times a plus b equals a squared minus b squared. Now, we're going to use a Pythagorean identity, right? That, I think I've written it out this way. Sine square of theta plus cosine square of theta equals 1. That basically comes from this triangle right here, where the hypotenuse here is 1 from C to B. And then C to D is the cosine of theta, and from B to D is the sine of theta, and then just apply the Pythagorean theorem to that. Cosine square of theta plus sine square of theta equals 1 squared, which is 1. Okay, and then what we do is we then take that expression and just solve it for, solve it for cosine square. So cosine square of theta equals 1 minus, 1 minus sine square of theta, and then add negative 1 to both sides. We get cosine square of theta minus 1 equals minus sine square of theta. And the left side right here is what we have in the numerator down below. So we're going to replace it with the right side here. And that's what we do in the step from this step to this one, from the second line to the third line. Okay, now what can we do? You still plug in x equals 0, you got 0 is 0. But what I can do is group this together. So this is a negative 1 and a sine of x and another sine of x multiplied together. I'm going to think of that as putting the sine of x over this x, put the negative sine x over the cosine x plus 1. So break that into two parts. Now, the limit of this product is the product of these two limits provided both of these limits exist. This limit on the left is 1, which is what we just proved just a minute ago. Now, when we plug in x equals 0, we see this is a continuous function. It's made up out of continuous function parts, and we do not get dividing by 0 this time, so we can just plug in 0. Sine of 0 is 0, the opposite of that is still 0. Cosine of 0 is 1, plus 1 is 2, 0 over 2 is 0, and 1 times 0 is 0. So, we know that the limit as x goes to 0 of cosine x minus 1 over x is actually 0. Now you can see that from the graph as well. If I graph y equals cosine of x minus 1 over x, I get a graph that looks something like this. By the way, as you're going further and further to the right, it's bouncing up and down forever, but less and less. But look right here, what happens here close to the origin? It actually comes in toward the origin as a limit point there. It's a hole in the graph. And so we can see that, and of course we can look at tables to corroborate that as well. So, net result, we've got a couple of important limits here. The limit as x goes to 0 sine x over x equals 1, and the limit as x goes to 0 of cosine x minus 1 over x equals 0. And these two results are very important steps in the proving and finding what the derivative of some of the trig functions are, particularly the derivative of sine of x. And then cosine x will kind of come from that as well.